Thank you very much for the invitation. It's my first time on Schiappa. Here. So, let's see, how long am I supposed to speak for now?
For 1 hour, but we're very flexible.
Okay. No, that's fine. I'm going to try to do this at a very surface low level, but if you guys think that you want higher level, just ask. So, I mean, it's important to interact, right? Because I don't know exactly what you want or you don't want. So, make questions, say we want harder stuff, say we want easier stuff, whatever. I mean, it's easy to adapt. Okay? So, let's see. I want to tell you about some things which go by the name of resurgence. That's one of the key words. And transseries. That's another key word. But they're very much related to each other. So it's not like they exist independently. At least not from the point of view of what we want to talk about. So what's the idea here? You know, let's imagine that you have some problem that you want to solve. And I don't care, this is something which is applicable to quantum mechanics. Let's say you want to compute the energy of the ground state of some complicated potential. And this is going to be something hard to compute generically. I mean, I'm not talking about harmonics. Let's imagine we're doing particle theory, and I don't know, in HD you want to compute the beta function. Beta function, if I ask what's the exact value of beta function, might be a hard question. Let's imagine we're doing string theory, and you want to compute, I don't know, free energy of some string, AES background, whatever. Generically, it's also hard. So there's situations where we know how to compute these things exactly, because they have lots of symmetries, and they make the problem simpler. And then I say, okay, I know how to compute an energy, beta function, energy, or whatever, it doesn't matter. I mean, for the moment, I could be thinking of any observable that I want to compute in any kind of field. But generically, I don't know how to compute this. So generically, what I have to do is, if I want to compute some observable, I have to pick an adequate coupling constant, which, of course, in which I'm going to do perturbation theory. And so I'm not computing the exact result. What I'm computing is an approximation to the exact result. And generically here you do expansion H bar, and here, well, it's complicated, whatever, G string, that's what I want to use. I'm not going to talk too much about quantum theory because the normalization brings in some extra details. Alright, but perturbation theory is great, but it's an approximation, right? So let's just give some numbers and some names to things. And let me call my observable here, just call it phi. And I want to compute phi, and I'm going to write it as a power series. So it's going to be approximate. In some coupling, for the moment, let's go with H1. Let's imagine that I'm computing. And K would be the order, the kth order in H bar at which I'm computing. It's okay, great. So now I can go order by order, compute these phi k's, and see what can I do with them. That sounds great until we realize the following problem. And this is what's the starting point of the story I want to tell. Is that these phi k's, the kth order contribution to my observable phi, they grow as k factorial in most interesting problems. So if they grow slower than factorial, your problem is in some sense too easy. So generically, they grow as k factorial. And why is that a problem? If you compute the radius of convergence of a power series whose coefficients grow as k factorial, is zero. Does not converge anymore. And this is not anything related to weirdness of quantum theory. This is a generic statement in which applies to many of these problems. So you say, what the hell am I going to do with perturbation theory? Because it doesn't converge anywhere. So, I mean, if you want to compute the energy, what's the value of the energy? You know, I'd like to go to the laboratory and measure something. That's one question. And the other question is, what I'm doing here is perturbation theory. Yeah. But if I'm computing something exactly, I'm expecting that it will have two contributions. It's going to have a perturbative contribution, but it's also going to have a non-perturbative contribution. So where do I see the non-perturbative content coming in from the point of view of this power series that I just wrote here? And the first clue is, let's look better at how these guys grow. And it turns out that the way they grow, I'm just going to give you the next. So at leading order, they go as great factorial. And at subleading order, they have exponential growth. The exponential growth at subleading order will be something like this, where A is, for the moment, a number. And the reason why this is going to be connected to, just get some colors here. The reason why this is going to be connected to the non-perturbative contribution to whatever observable I'm trying to compute is because this A, which I have here, is going to be an infinite action. It's not by accident that I'm putting there the letter A. And this is going to allow the fact that next to leading order I see an instantaneous action is what's going to make the road back to non-perturbative physics. Yes.
How generic is this factorial k divided by a to the k is? I know the argument typically from counting Feynman graphs.
Yeah, but this is a bigger argument than counting Feynman.
So what is
diagram.
Can you
Because
tell
let me
us
say,
quickly if it's not possible, we'll talk it later.
no, it will become clear in the lecture, so you will see. I'll come to that. But let me just make one remark that this class of problems that we're generically interested in, and most of the time I'm going to be talking about them. This statement is a mathematical statement which is generic. It has nothing to do with quantum mechanics. This would be true in perturbation theory and classical mechanics.
But it has to have some assumption, because I also know counterexamples to this.
Usually the counterexamples will be too simple.
For example, planar diagrams. So if you count...
No, but planar diagrams, they come from... That's too simple, because
yeah,
planar diagrams... Okay, so Frank is suggesting that we look at some subsets of problems than the ones that I'm trying to classify here. And planar diagrams, which let me put in a side here, that maybe you guys have heard about, diagrams that look like that I can draw with double lines on a plane. If you look at their growth, let's say that you're looking at computing, I don't know, free energy, whatever you want to compute, it's going to be exponential. It's not going to be factorial. So it's going to have a non-zero radius of convergence. And in fact, you know that. That's the point where you do the double scaling limit. So then it's simple. So I'm not saying that every series is divergent. I'm saying that series of this class have a zero radius of convergence. They're divergent everywhere. And then this statement is generically true. And you'll see this later today or maybe tomorrow. All right. So, yes.
Is it clear that in every problem is phi k? This is a series.
Every problem is?
In every problem that is phi k are always positive, that can always be this kind of argument. Can't it be that there are positive and negative cancel out?
There can be. But again, this will be simpler. So I'm just trying to tell you what's the hardest thing you can find. And then, of course, from there, we can deconstruct and look at simpler stuff.
And can you make this last statement that you use in the statement about insular or something?
It will come. So right now I'm just trying to give you, so my idea is to give you some ideas. Some of them will be clearer than others, some will be a little bit blurred, and then we'll go in circles talking about the same things until it becomes clearer and clearer. Okay? So let's So the structure, again, this idea that we're going to go in circles, let me try to give you an idea of what's the structure that I expect to find. So when I'm trying to compute that observable up there, which has this structure that I wrote, and I know that these guys, they grow as k factor. And I know that they have the subleading growth, which I wrote that in red, of A. Instanton action to the power k. So what that is going to imply is that what I'm looking at here is my perturbative contribution. So the initial power series I start looking at is perturbative, so I'm going to put it at 0. And I'm still missing the yellow non-perturbative contributions. So there must be something else that I need to add here in order to start making sense of what perturbation theory is. And what I have to add here is something that schematically has the usual instanton-like exponential contribution, something that looks like this. These are non-analytic contributions. They are exponential of -1 over h bar. They're not analytic like this. And at a fixed instanton sector, and what do I mean by fixed instanton sector? I mean that I could have different instanton numbers playing a role here. So I'm going to put an integer there, n, and I'm going to sum over all these instantons. I can still have further fluctuations. I mean, I can compute loop corrections around a fixed instanton vector that would look like this. Where now this is the nth contribution. That's an nth contribution. Okay? So the non-perturbative part is actually, in some sense, larger even than the perturbative. There's lots of people. So the kind of the idea of the solution that perturbation theory, and by perturbation theory, when I'm starting to think about including all these people, I'm starting to think about using perturbation theory to obtain exact results, is that there's going to be a bunch of people. There's going to be my initial perturbative guy, and then I'm going to have the 1 instantons, the 2 instantons, the 3 instantons, and so on. This is what was it called? So this is the 1, the 2, the 3. This is the whole structure which is encoded in this object. And this object, where I have analytic people and non-analytic people, is what's known generically as a transseries. It enlarges power series. Usually I think of power series as stuff made of powers of some x. And now I'm using powers of a monomial to construct a series, I'm sorry. I will use powers of a transmonomial to construct a transseries. And what does a transmonomial look like? Stuff which is non-analytic. Here's one example. And I can use powers of this. Here's another example. And I can use powers of this. None of these guys is analytic at the origin. But I can start iterating these people, and here's another example. I can consider the exponential of the exponential of the exponential of the exponential of -1 x, or I can think about the log of the log of the log of the log of whatever. And there's a general statement that says that if I stay within this class of iterations of exponentials and logs, I pretty much am going to nail every problem you can think of. At least the way the statement is done is that I'm going to nail any natural problem, any problem which has a natural origin. Of course, mathematicians are very good at coming up with non-natural problems, which will come outside of such classes. But that's not the whole story of transseries. So we already know that this guy here is growing as a factorial, and subleading has some information about the instantons. So what's going to turn out to be the case is that I can use all these power series that are given here. And all of them, their joint contributions are going to tell me how is this guy growing. So there's going to be more stuff here in the growth. And these dots, which I'll make explicit, contain information arising from all the instanton sectors. And so if I know all these instanton sectors, I know more and more contributions to the large order growth of the perturbative center. And the more I know about the large order growth, the less this is a statement about large order growth, and it's a statement about the exact components. So if I know everybody, I know these guys exactly. But there's, of course, the inverse map, which tells me that if I know these guys exactly, I can point the arrows the other way around. And this means that if I know the perturbative exactly, I will know everything about the non-perturbative. So when I have here perturbative plus non-perturbative, what I really want to have is an arrow in between, because if I know one, I will know the other. And that is the content of resurgence. Okay? So this is the idea. And now we can make it more precise.
So I have one question at this stage. Assuming
This is very vague. But
yeah, so assuming what you said, and there's some assumptions that probably are more clear. But so if you have perturbative plus non-perturbative, it still doesn't mean that you have the exact result, right?
What do you mean?
Because each term is still divergent.
Yes, but then, okay, that was...
So exact is beyond non-perturbative in this sense.
No. So, in order that, okay, if I give you, let me add something to what Frank is saying. All these guys are also divergent. They're all asymptotic series. So, there's two issues here. One is, when is the asymptotic information enough so that I compute an energy or whatever? And in order, so how much information do I need? The principle information I need is this. And then the question is, okay, now I have that information, how do I compute the number? In order to compute the number, you have to use a trick that we'll get there, which is called Borel resummation. Okay? If you have all this information, Borel resummation will work. If you don't have all this information, Borel resummation won't work because it will lack stuff that you need to feed in, as I will show you in one or two lectures. Any more questions on the idea?
So like some sort of complete basis of these non-analytic functions in which we will expand or?
Yes, pretty much. So that's the statement again. If you consider that class, so basically, you have names for these things, I maybe get there now. You talk about transseries with specific exponential height, depending on how many exponentials you iterated, and with specific logarithmic depth, depending on how many logs you iterated. And so, different classes of problems require different transseries heights and depth. And most problems actually require height 1 and depth 1. But there's hints already of height 2 in the SYK model, I think Frank will talk about at least the SYK model. And getting iterations of log was kind of appears all the time. I don't know, any first.
Is there like some guarantee that these different depth things won't mix with each other ever?
No, everybody mixes with each other. So that's the story of resurgence. All these arrows, that will show you some more complicated things, are all going to be mixing with each other. So the good thing is that if you know one sector exactly, you have access to all others.
Exactly in the sense like the full power.
I need to know all of them. The more I know, the more I can access. So you can get, let's imagine that up there, I don't know, up to 10 loops. And you don't know more because it's just too hard. You won't know the exact non-perturbative data, but you will know a lot about them. And you will know instanton actions, you will know the first loop corrections about the one instanton sector, all these things are cool. If you have more and more, you have to produce more data. So there's, of course, there's always a trade-off.
Schiappa, you don't even know whether instant on, given in some arbitrary random problem, would there be instant on or not, right?
So that's one question that can happen, is that I set up this construction. You make me a question in one of those problems, I start doing the calculation. And then I say, well, you need to have an instant on action, which is square root of 1. What's the instant on that gives that? You may not know. We have problems where we don't know. We know that they must be there, we don't know what is their physical description. Okay, so next layer of complication. Let me erase this. Yeah, this is not. Let's make these things slightly more precise. Let me call my observable by phi, as usual. And let me use the coupling constant to be x. Okay, so then you select which is your favorite bar. You want to put an h bar, you want to put a g string, whatever. So. And I'm going to be doing perturbation theory close to the origin. Not necessarily this is always the case. In large n, you do close to infinity. That's fine. Let's imagine I start computing my perturbative. I'm going to put 0 for perturbative all the time. Series. And I'm going to use this sign, semi-equal, to say that whatever I have on the right-hand side is an asymptotic series. So the coefficients grow fairly fast. It's not per se a well-defined object. And the statement of being asymptotic is the one we already discussed. These guys grow fairly fast. Alright, so now we're going to try to answer Frank's question. I want to see a number, I don't want to see a formal result. How can I see numbers? Well, one way is to realize that, as I just said, that there is subleading exponential here. So if I had something which only had exponential growth, it will have a non-zero rate of convergence. It might be small, but it will be non-zero. So why don't I just try to get rid of that factorial and see what I can do? So there's a machine which is called the Borel transform. And what this machine is going to do is precisely that. It's going to remove my factorial. We'll just see what conventions I'm using here. So B is the machine, the Borel transform. It grabs something which is expanded in monomials of x, so my coupling constant. So let's say x and it is a function of x. So here x is the coupling, which I am now going to think can live anywhere on the complex plane. Let me not be too restricted to the real line. And s is where I'm mapping stuff to, and I will call s in C as the Borel plane. And what this machine does is just what I said. It's removing the factorial. And notice that the way I've written here, it works for alpha non-integer.
Could be the growth is faster than factorial?
There could be, and then you have to adapt, but that's fine. The whole statements remain. I mean, it's obvious where you have to change stuff. So, if I have to compute the Borel transform of my series, if I'm computing Borel phi naught of x is a bar series in s, I am expecting this to have a non-zero radius of convergence. So let me draw the S-plane. This is the S-plane of that Borel. And I'm expecting that, generically, this Borel function will have singularities on the Borel plane. But I'm expecting that there will be a finite distance away, so the closest point to the origin will be a finite distance away from the origin. So I can define my Borel transform in this circle, in this disk, and I can then monolithic continuation and try to go elsewhere on the complex one. So, okay, that's great. So I know something here in this disk. What can I do with it? Because I wanted to compute something. How can I get that number out? Well, let me try to play this game. Do the Borel transform. I compute the power series in this disk, and then I do monolithic continuation. Let's imagine I did this. What can I do with this function? I can try to do the inverse Borel transform. That's sort of the natural expectation. And the inverse Borel turns out to be, it's not too hard to see why, there's a gamma function here, so it has to be sort of a Laplace integration so that I can take the inverse. And the inverse is going to be denoted in the following way. So it's phi naught of x. That's what I want to compute, right? So if I'm doing the inverse, I'm expecting to get back to phi naught of x. But it's resumed. I'll see what the meaning of resum means. I'm going to use the curly s here. It's going to be a resummation because I went through this process of doing Borel, getting back. And this is given by an integral, which looks like this. It's an integration over the variable s of my Borel transform times, I need to bring back the gamma function, an exponential. Alright? And where am I doing the integration over? I am doing the integration starting at the origin. So it's a ray. And most of the time, people do the integration over the real line. But I don't actually have to do that. If I really want to go non-perturbative, I should be able to go anywhere. So I'm just going to consider a resummation over some ray with angle theta, and I'm going to put the theta there to say that there's many resummations I can consider. Some will have more complex data, others will have less complex data. By complex, I mean complex numbers. And then you can see why, when Frank was saying, yeah, but they're also that I can do Borel, I get a number. Why that's not enough information. Because I can vary theta. And as I vary theta, as you can see already in that picture, there's going to be some instance where this ray is going to have to decide when it goes around, let's call this theta star, the angle where it's hitting the singularity. And I'm doing the inversion. I have to decide if I'm doing the inversion avoiding the singularity through the right, and I could call this f theta minus, or if I'm avoiding the singularity above, and I could call this x theta plus. So you see that there will be a difference, and the value of the difference is given by that singularity. And this is a generic statement, because if there are no singularities on the Borel plane, this means that the original series you started off with was not asymptotic. So asymptoticness requires that Borel is not entire. So this problem always arises, and then the question that you have to answer is, how much is this difference? Because it may play a role. And generically, this difference is the transmonomial that tells you that there has to be instant-time correction. Okay, let's make this even more precise. Is this clear so far? Yes.
Let's say you had a transseries with heights 2.
Yes.
Would you get differences that are...
It's, again, I'm just going to do everything for height 1 and depth 1. All these things should be adaptable, and they go with these questions. So, what if the grossest facts of the factorial? I will have to change my gamma here, and so on and so on.
But would you always tell what terms appear in your transseries by looking at
Yes.
this?
Yes. Yes. That's right. That's right. And there's a whole theory of these other possibilities to consider here, which is known as multi-summability, but I will come to this later. Okay, so let's make this slightly more precise by telling you something obscure, which is the following. It turns out that we'll go in circles and we'll make this precise. It turns out that this question here has a generic answer, which for the moment we'll say that's not an answer because it's not telling me anything, but it will become an answer, which is that the resummation above is equal to the resummation below up to something which has this weird symbol, which is known as the Stokes automorphism. So far I didn't actually tell you anything, but we will grow to understand what is the Stokes automorphism. This is the basic object. It's known as the Stokes automorphism. And the reason why it's known as Stokes, of course, has to do with the fact that it will embody Stokes phenomenon. So, 2 centuries ago, Stokes wanted to understand the colors of the rainbow using the Airy function. And the Airy function on the positive row line is an exponentially decaying function. But in order to explain the colors of the rainbow, you have to go to the other side, where it has to oscillate. And the series that he was computing was not oscillating. So there's something else that was required, which was a different exponential that they could combine to oscillate. And so this is sort of the modern day version of what Stokes phenomenon is, and we'll get. So far, in fact, I haven't told you anything except gave you a weird symbol to explain the formula above, but we will get there and we'll understand what it means.
So are these similarities always poles of some order, or?
They're not, rarely they're poles. Generically, they're branch poles. As we will see, there is a way to organize all these structures so that they will generically be logarithmic branch poles. If they're poles, and somehow they're too simple. This happens in some supersymmetric cases.
And then these symbols that you are written down, these are just integrals of your
We will get to what this symbol is. Right now, I just want to, again, lay an idea of why it has to appear somewhere, and then we'll get to what it is. All you have to understand is that if I know the Stokes automorphisms of all those singularities, then I know how to glue everybody together, and I can go around. And I'm done. But I still need to tell you, of course, what these objects are. I will come to that.
It's true that there always exists a ray along with.
Sorry, I didn't.
So with this Borel transform,
Yes.
if there were no singularities,
No, there was always some similarity.
if the thing is asymptotic, if the original series is asymptotic, then there are always similarities.
There must be some similarity.
But if there were no, it will always be the same answer back, right? If you do this step process.
If there's no singularities, then you don't bother to do this, because that means the series is asymptotic.
It's not asymptotic, but what if I follow this procedure?
You need nothing, you waste time.
It is the same thing.
Yeah.
It is the same thing. But is this true that? Okay. So when you rotate your ray, this will pick up contribution from these various singularities, and the answer across the singularity would be different. But if any of these rays, is it true that every possible ray gives you some finite answer, or
Yes.
every possible ray gives you finite answer?
Yes. Once you play this game properly, you always have some answer. Then there is yet something that we'll get to, which is understanding which is the one that has physical meaning for the problem you're studying. So right now I'm just telling you what's the mathematical structure. But let's not get ahead of ourselves. Let's keep going here. This Stokes automorphism, again, I will write another mysterious formula, and I don't know, maybe even today or perhaps only tomorrow, we'll be going through explaining what all these mysterious formula mean. Can be written generically as an exponential. Okay, I have to erase this. The formula is too large for this corner. Sorry. So it's written generically as the exponential of a sum over the singularities that I find along theta. Generically, I can find several singularities. Here's what the generic theta direction looks like. This is the S-plane. This is the generic singular direction, not theta. Along theta, I'm generically going to have a bunch of singularities. Okay. They usually align along rays. The reason why they align along rays is because then they're the multi-instanton singularities. Different instanton actions may point along different directions on the complex plane, but then if there are multi-instanton actions, they're going to be just the generation of singularities along those rays. So it's a sum over this omega theta. These are the omega thetas. And just write them generic of this, again, I'm not giving you a lot of information because I'm replacing symbols by symbols. Alright? Where this object here that I just replaced is something known as the alien derivative.
Is this dependent on x?
Sorry?
Is this dependent on x?
No. The name alien comes from French étranger, so it could be translated as foreigner, but it ended up translated as alien. It's just because many people are puzzled why this alien goal. It could also be translated as outsider. So these are different. This is the work of the French mathematician Ricardo, and it was translated like this. So far, I just replaced a symbol by a symbol, but at the same time, I've given you information that you knew that had to be true. If I call this guy an automorphism, it has to be the exponential of the derivative. This is, if you remember your basic algebra course. If this guy is an automorphism, it must be the exponential of some derivative. And so part of the game here is trying to understand what is that derivative? Where does it act? It's just going to be working on the Borel side. So it doesn't have any x dependencies or x. It's just going to be looking at what the structure of similarities is. And if I know the algebraic structure behind this guy, I am able to construct this guy, and I am able to answer my original. Okay? Again, these are just names that are a bit vague, but these things will become more precise as we go. So now I know that if I cross a singularity on the Borel plane, and I'm trying to do the resummation to get some numbers, I need to include some other people that I had not looked at before. And perhaps the answer to those people is in these objects, the Stokes automorphism, the alien derivative, but because I didn't tell you yet what they are, let's not assume the answers are right there, right now. So let's just ask, what the hell am I going to do if I found an exponential and I didn't start with an exponential? And so the answer is, I already told you, I need to enlarge this into a transseries. So what I should have actually started off with, to make sure that every time I give a term, I know where I'm going to end up with, I should have started with a transseries. So what I wrote just above this blackboard, that phi 0, should have been a phi, not 0, because it should include all possible non-analytic exponential contributions. It still depends on x. Might depend on something else in a second. And this now, I'm going to be brave enough to put an equal sign, because I'm hoping that this will be the final answer to the problem. It's going to be a sum 0 to infinity, of all the people I should have considered. Not just the phi 0. Of course, when n is 0, I get back what I started off with, but when n is not 0, what these phi n's are these contributions. Okay? Where A is the instant on action, N is the nth instant on sector, and all series here are still possibly or generic asymptotic. There's a couple of extra details that I still need to add. The first is that not all series start at 1. It turns out that there could be some shifts. This is just a technical. Some series, they only start at 2 or at 3. It turns out that there are cases like that. And the other thing is that I still need to include some sort of instanton counting parameter. I will call it sigma. Power n. So this sigma is a variable which is known as the transseries parameter. And what does it do?
Oh, sorry. Just a small question before we move on. Your shifts beta n cannot be negative? It can never-
Yeah, it could.
So it can start with negative power.
It could start.
In the instance.
Yeah.
No,
Okay,
it's
some
just-
cases, that's in matrix models in some cases, it does, when you look at instant on center. Let me try to explain what the transseries parameter is doing, because it might seem weird. I mean, its obvious role is not weird. Its obvious role is to count. You know, if I think this is a generating function, it's counting how many instantons am I considering at each n well. What it's actually doing is it's encoding boundary conditions. So what do I mean by this? One way, or in fact, the historical way, where transseries appeared was not in quantum mechanics or field theory or string theory, was in the theory of dynamical systems, where I'm studying an ordinary differential equation, or a linear ordinary differential equation. And, you know, again, there are very few exact results from that, and that's why the whole field developed. And people do perturbation theory. And one thing that we all know is that if I write down for you a differential equation, it will have, and imagine that I can solve it, it will have a general solution, and it will have particular solutions. And in order to go from a general solution to a particular solution, I need to fix my boundary conditions to these answers. So generically, when I solve the differential equation, I have a family of solutions. And this is also true here. So basically, that's what sigma is doing. Sigma is telling me what is the family of solutions to whatever problem I am addressing. And different choices of sigma will be corresponding to different choices of boundary conditions to my problem. So again, if I'm solving a differential equation, I can, you know, let's imagine it's first order, I need to say, what's the value at time 0? Or if I'm studying an integral, I also have a freedom of boundary conditions when I say, what are the contours of integration that I'm choosing? I don't have to do all integrals from minus infinity to plus infinity. And in particular, this is relevant in field theory, when you write down a functional integral. What is the space over which you're going to do functional integration? You can choose different slices of this space, different contours, and they need to be parameterized by something. And that's what this sigma is doing, is parameterizing boundary conditions.
Is it a real number?
Say again.
Is it a real number?
It can be anything. At this moment, it's just a label for the family of solutions. Depending on, then you say, okay, I want to solve a physical problem. I need to specify what my sigma is. I need to specify what my boundary condition is. Now, you could say that from a mathematical point of view, it can be anything. I mean, I can imagine, you know, grabbing a stone and throwing it up in the air with initial speed I. That's fine. It's just not very physically sensible. The same thing will happen here. Again, in fact, to answer the question you asked before, there's some art in deciding what is your physical problem, is understanding how to choose your boundary condition to answer the question you have to start off. But for the moment, from the point of view of transseries, we get And the last thing I want to tell you before we start digging into an example and having this be too abstract, is that this transseries parameter, which is this boundary conditions, is very much associated to that Stokes automorphism. In fact, here's a very modern way to write down the solution to Stokes' problem. And I'm just going to write it first, and then I will explain it, because it will become very clear. That's the problem that Stokes addressed 200 years ago, less than that, 2 centuries ago, to explain the ring. So let's imagine that we are on this setup. Let's understand what this formula means. And let's imagine that sigma is set to 0. And I am on this side of the equality. If sigma is 0, as you can see from this expression, there's no exponentials. All I have is my original power series. And that is not going to explain why the area function is oscillating on the other side. I need to find an exponential somewhere. And so what Stokes does is he starts going around the complex plane. And then he says, oh look, there was an exponentially suppressed term that I didn't see because I was just doing Poincaré power series. And the exponentially suppressed guy is more suppressed than all my knowns. I have to grab it, and I have to take it along. So he grabs it, he takes it along. And when he arrives on the other side, it's of the same magnitude as the original power series. And then it changes physics dramatically. Now the area function is oscillating. That's what happened here. I start with sigma equals 0. I only have the power series. And as I cross the Stokes line, as I cross that ray on the Borel plane, in here I put plus and minus, no matter what theta is. I need to grab the singularity. The singularity is that exponential term. And I need to grab it along for the ride. And this is done by the Stokes automorphism and by the alien derivative, in the sense that the alien derivative is going to act as a translation in sigma space. So that sigma is going to jump by a number. And this number is what's known as the Stokes constant. And this is the hard thing to compute. Given any problem, the hard thing to find is the Stokes constants, because it should be sort of vaguely clear that if I know the Stokes constants, I know how to jump around and go around the complex. Yes?
So if you have many singularities along
Yes.
the same line, then you have many possibilities how to avoid singularities, right?
You have.
Then you have not only just S plus S minus, but you have many possibilities.
That's the power of this object. The way this object is defined is as a weighted average, and I'm not going to talk about that, is not just defined as a, you could think that this object is sort of an average between the plus and the minus, but it's more than that. It's an average over all possible contours that I can think of. So that's taken care of. That's the power. That's why people introduce all these formulas. It's because the object which behaves as a derivative is, and this unique object that behaves as a derivative, is the one that already takes that problem into account. If I were just to do the average between the plus and the minus, that wouldn't act as a derivative. It would not satisfy Leibniz.
When you say derivative, what do you mean derivative with respect to what?
We'll see that. So again, as I tried to convey here, the idea is that it's going to act somehow in sigma space. It's going to act on the moduli space of solutions to your problems. It's going to be a derivative. It will become more clear as we go for the second round or third round already. Any questions here? All right, now let's see an example where we're going to make all these things very precise in an example. Because, again, the general definition of all these objects is extremely complicated. It takes a lot of time. So, I mean, we're going to now, we sort of have an idea of what these objects are, and now we're going to see how to define them in a simple example. simplest possible example I can think of, which has some physical motivation. I'm going to consider what I call, with quotation marks, quartic partition function. In short, this is a second year undergraduate problem, which is compute for me, if you will, the following partition function. This is a one-dimensional integral, as toy model as it gets. Okay? Everybody knows how to compute this, right? Now I want to know how to compute this using the ideas that I've just described.
So why do you put a minus sign? It would be more natural to put a plus sign.
I don't know, that was the
If you integrate from minus infinity to plus.
Well, let's start by the, yes, Frank is complaining that I didn't specify what gamma was. That's for a reason.
Yeah. But if you do the
Let's allow,
naive thing, and then
yeah, let's allow for anything. So, let me try to make a plot here. If I plot, let's see if I can do this plot. Sorry for my drawing skills. So what I'm trying to plot here is the regions of positivity of the potential. And in yellow, it's where the potential is positive. And the rest is where it's not positive, okay? With the choices, for this plot I'm going to draw is lambda equals 1, at least the one that's in the legend. And, of course, if I want to define what a gamma should be, it must go from a region for convergence of the integral alone, with the choices I've made. These are the possible contours of integration I can have. There's 4, only 3 are homology independent, only 2 are actually independent because the potential is still Z2 symmetrical. Anyway, those are the. Is the red clear on top of the yellow? Sorry, that was not the best. Well, I think it is. Alright. How can we solve this? What we're going to do is to do just two simple, very simple steps. The first is I'm going to change variable, just not to carry h bars around in lambdas, because it's not too hard to see that if I write x equals lambda times h bar, then this becomes the following function of x. So there's basically only one independent variable and not two. Oops. Right, so all the dependence of this function is in x, which is there. The h bar is trivially a square root front. I'm going to forget about it. And I'm going to notice that this integral satisfies a differential equation, which is this differential equation. It's second order. Which means it's going to have two solutions. It's linear, which means I could just go out and solve it and not care about resurgence of transseries. In fact, that's a modified Bessel equation. But I'm going to imagine that, no, Bessel, I never heard the word Bessel before. I'm going to keep going with what I know of resurgence and transseries and try to solve it. And in particular, if it's second order, it's going to have two integration constants, two boundary conditions, which hopefully will, encode what are the choices of contours that I could have made in that initial integral. All right, let's try to solve it using these methods. So the first thing is I'm going to imagine the following ansatz for a solution. It could be a power series. We already know that we're trying to do perturbation theory all the time. But we also know that exponentials may come up, so let me also put an exponential here. Like that. Plug this back into the equation. What comes out? The first thing that comes out, and now I'm doing perturbation theory, so I go order by order, solving this iteratively and seeing what comes out. The first thing that comes out, A is either 0 or 3/2. That's not a big surprise. I could have computed here the solutions to the vanishing of the derivative of the argument of the exponential if I wanted to do steepest descent. And then at those solutions I could evaluate the potential and I would get this to know. So that's not a surprise. But it's good to see that it's a nice consistent check. Alright, let's go on. Let's not go step by step, but let's go all steps straight and let me give you the answers that we had. So you're going to have a power series associated to A equals 0, which looks like this. And I'm going to have a power series associated to A equals 3/2, which I will call phi 1. And by 1 I'm thinking of one instanton, quote unquote, which looks like this. And everybody is known in closed form. The reason why everybody is known in closed form is because it's a linear equation. If this were a nonlinear equation, I would only compute a couple of these guys. By hand maybe 2 or 3. In the computer, the nicest example we have for non-critical string theory, the 1,000 of those terms in the computer. But anyways, this is linear, so it's easy, and so coefficients z of 0 look like this. Let's look at some numbers or some expressions. And the 1 look like this. And you can already see a lot of things. From the ratio of factorials, you can see that the growth is factorial. It's basically 4 minus 3, 1, so it's n factorial. And what's the subleading growth? Can anybody tell me what the subleading growth is? So here's the leading growth. In both cases it's the same, which is n factorial. And there should be exponential subleading growth, which should be dictated by the instanton action. Right? That's divided by 8 to the n. So you already see all these things appearing extremely explicit. There's a couple of numbers there. Let me go connected there. These numbers is basically h bar over 2 bar. They're not the same, up to a factor of 5. It's just a normalization of it. This doesn't matter. So the content is all in the big stuff surrounded by yellow. So now I see that the structure I was expecting is already there. Can I see more? How long should I go on for? I mean, I have like 1 minute, so should I stop immediately, talk for 5 minutes? Or?
No, I could stop where you feel most comfortable.
No, but it's up to you guys, because I don't want it to be not paying attention.
How's concentration, guys?
Can I talk for 2 or 3 more minutes?
5 minutes.
Okay. So now I have those two ansatz of solution. So I can, again, I have a linear differential equation. The space of solutions is 2-dimensional. So I want to create a basis for the space of solutions. And I can use those two ansatz as my basis. So I'm going to use one element of the basis of the space of solutions, Z0, and the other one is Z1. And they're just the obvious things, right? Z0, let me not write everything again. It's basically phi0, and Z1 is basically exponential of minus x over x, a over x, where a is already given that side. Right? So what's the general solution? The general solution, which I will call Z, curly Z, depends on the coupling. And it depends on two transseries parameters, sigma 0 and sigma 1. These are the boundary conditions of my differential equation, such that this is equal to sigma 0 Z0 or sigma 1 Z1. Here's my transseries. It's a linear problem, and the linear problem implies that the transseries has a finite number of elements. If the problem were to be nonlinear, this transseries would keep going, like in some formula that hopefully you wrote down and that I wrote earlier on. There's an infinite number of instantons in nonlinear problems. There's a finite number of instantons in linear problems. That's the main difference.
Just by looking at the original integral, how do you figure
Sorry,
out?
sir?
Just at looking at the original integral for the variable that you are computing, how do you figure out whether it's linear, non-linear, or what? Do you just try to do the b prime equal to 0 thing and find out?
No, one way that you could do that from the original integral is that calculation there in yellow. You compute the stationary points, and you get 0 and 3 halves.
So the number of these cell points will always be equal to the number of these cell points of this potential.
Alright, so last thing is, yeah, you said that there was a transseries that was cool and all, but everything seemed to be in the Borel plane. So can I compute the Borel transforms of these guys? And what structure do they have? Well, yes. Actually, it's not too hard. Because I have exact expressions for all the terms in the asymptotic series. So I can compute the Borel of phi 0 in the S-plane, and it looks like this. 1/8 h bar over 2 pi square root. That's just that Z0, that's just the constant which is there in blue, times the 2f1 hypergeometric. That's kind of nice, because now I know how to define, I know how to evaluate my Borel transform everywhere on the complex plane. And I know that it has singularity with a branch cut. That's what I expected. I can do the same thing for the Borel of phi 1. And I find whatever, something which looks very much the same. Let me just write that. All these calculations are very simple. In fact, mathematically evaluates this in 2 nanoseconds. And now we know that there's a branch cut going from z equals 1 to plus infinity, which means in this case going to from 3 halves to plus infinity. In this case, minus 3 halves to minus infinity. Well, okay, you can orientate it the right wherever you want. That's the idea. What happens, let me just finish with that. So that's something for you to think about for now. What happens if I look at the structure of these Borel transforms close to their singularities? And it's quite interesting. If I expand this one, close to its singularity at s equals 3/2, what I find is the following, and this is basically the answer to all the questions that you had when I was writing weird symbols before. There's a pole. And there's a logarithmic branch cut. And there's holomorphic stuff. Okay, which I don't care about. I'm just trying to see what's the structure next to the singularities. And there's something there, of course, I left room here for something. What's the structure of the other one? Wait, if I can find it. It's this one. Looks very similar. Now it's at plus a instead of minus a, which means basically that I'm doing the expansion here is that s equals minus 3/2, right? That's where that singularity is. Plus minus 1 times the log, there's a log branch cut, plus the holomorphic stuff I don't care about. Alright, so you say that's interesting because, okay, this is a very simple problem, but this is actually a rather general statement that I'm going to say. This structure is universal. It doesn't matter if you're doing a linear or non-linear problem or whatever. This structure, when you look at the Borel transforms close to their singularities, this is always what you find. And what do you find? You find some numbers, which in this case is plus 2. In this case, it's minus 1. And these numbers here, I can't compute them because it was a linear problem. But generically, they're the hard stuff to compute. These are the Stokes constants. And then, what is the function in front of the logs? It has to be something regular because the only singularity I said that existed is the log. What can it be? Well, can't be a whole lot of stuff because I don't have any more freedom in this problem. So it has to be, and here's the name, the resurgence of something that I have already seen. And what I find here is the Borel of phi 1 evaluated at s minus a, where it's regular. And in here, I find the Borel of phi 0 evaluated at s plus a, where it is regular. So, if I look at phi 0 asymptotic series, I compute its Borel transform, and I zoom in into the singularities, I find the resurgence of the non-perturbative content. And the same thing here. I zoom into the singularity, and I see the resurgence of whoever else should be there. And in this case, it's a linear problem, so I only have another guy to find. But if it's a non-linear problem, I will see the resurgence of everyone. And that's how perturbative and non-perturbative get connected. And I think maybe we should stop here. So next time, I will tell you that I can even abstract more than what I've done here. And I will abstract away from Borel into the alien derivatives. Basically, the alien derivatives will only enjoy this property. The derivative of phi 0 is going to be phi 1, and the derivative of phi 1 is going to be phi 0, and generically if I have a lot of p. And from there I can construct Stokes automorphisms, and I can start going anywhere in my problem for generic non-linear problem. So let's stop here. Any questions? Yeah.
Could you recall how this fits into the old picture in QCD with the instanton, the phenomenon?
It's just the same.
It's just
So,
the same, right? So
nothing. So if you want, this is the upgrade that should have been done in the 70s by Toth and these people, which ended up being doing by the mathematicians. You know, in the case of
So the
mathematicians next door. The renormal ones now are the role of the instantons. Right? Just because renormal ones are closer to the origin of the world plane than the instantons are in QCD. And so those are the guys that you should be looking at. But if you, let's imagine, and this is just at this stage a dream, I guess, that you solve QCD exactly, then you have all the instanton singularities, you have all the renormal singularities, you have infrared, ultraviolet, you have to take them all into account, and the transseries is going to be just a huge mess with everybody, and everybody's going to be linked to each other. But, you know, this is for 22nd century. More questions?
Can you continue evaluating the letter? Is that here these meant for different, but just for highlight that thing, you would have chosen anything in which that goes in two directions to infinity.
Yeah. So that's a basis. That's a overcomplete basis of
the combination of these things as well.
Yes.
Okay.
Yeah.
Any reference for people not working on this, where they can start reading about this stuff?
So I'm reading from some lecture notes that hopefully will be on the archive in the next couple of weeks, but last time I said this was a year ago. So right now there's 20 pages to go. It depends on how picky I get on those 20. But hopefully, let's say February, this lecture should be there.
Okay guys, I think let's take a 10-minute break. So we'll meet back at 10 to 4.